Welcome to the Level 3 video on an introduction to complex numbers. Today we're going to be talking about nth roots Okay, so let's start off this section by posing a quick question. What is the square root of I? So what I mean by that is there a complex number z, say a plus bi, that's equal to the square root of I? Or if we squared z, and therefore squared a plus bi, is there an a and b satisfy this such that when you square it you get I? This is the same question, I've just squared the expression above. So we can multiply out the middle part here and get a squared plus 2abi minus b squared, because we've got plus b squared I squared, is equal to I. And then we can compare real and imaginary parts. And the real parts tell us that a squared minus b squared is equal to 0, and the imaginary parts tells us that 2ab is equal to 1. And rearranging this, we can get that a is 1 over 2b, and then substitute this into the a squared minus b squared, we can get 1 over 4b squared minus b squared is equal to 0, and then times by b squared, we can get a quarter minus b to the 4 is equal to 0. And then solving this, we can get that b equals plus or minus 1 over root 2, but then we should multiply top and bottom by root 2 really, so we get root 2 over 2. And then when we substitute b into one of our expressions above, we can get back that a is the same, plus or minus root 2. So this means that our z, our a plus bi, was actually plus or minus root 2 over 2 times 1 plus I. And that means when we square this out, if we were actually to do root 2 over 2 times 1 plus I, all squared, we would end up with I. And the same with the negative. But the question is there an easier way? And the answer is, of course, yes, there is. So now we're going to derive a quick formula for the nth root of a complex number. So if we take our complex number z, and we write this now in its polar form, so we've got r times cos of phi plus I sine of phi. But then actually we want the nth root of this. So we take the nth root of this whole thing. The nth root. And then we can separate these out. Separate these powers out. So we have r to the 1 over n times cos of phi plus I sine to the power of 1 over n as well. And then we can actually use the fact that sine and cos here are periodic, with period 2 pi. So we can add on multiples of 2 pi here and it's still the same. phi plus 2k pi. Okay, and this is for k being some integer. And then we can actually go ahead and use Euler's formula, e to the I theta equals cos theta plus I sine of theta. Okay, so we're actually just going to just use this formula here. So we can rewrite this again, leaving our 1 over Rn at the front. Now we have e to the I phi plus 2k pi. And don't forget, this is all still to the power of 1 over n. And this is where theta equals phi plus 2k pi still. And using rules of exponents, we can incorporate the 1 over n. So we have I times phi plus 2k pi all over n. And then we can actually go back and use Euler's formula again. Now the fact that this n is incorporated into the exponent of the exponential, and we have cos of phi plus 2k pi all over n plus I sine of phi plus 2k pi all over n. And this is where we've set theta equal to phi plus 2k pi all over n inside Euler's theorem, inside Euler's formula. And let's go ahead and look at a quick example so we can see how we use this formula. So if the example is calculate the square root of I, so just exactly the same question we looked at a moment ago, our solution is going to be the following. Okay, so what do we know about this example? Well, n is going to be 2, because this is actually the same as I to the power of a half. So if the formula reads z to the 1 over n here, then this can be written as I to the power of a half. So n is 2. R we need to know is the modulus of z. Don't forget that z is I, so this is going to be 1 squared plus 0 squared square rooted, which is 1, because we have 1i. K is going to run between 0 and n minus 1. So we're going to have 0 and 1. And phi is the argument, so that's going to be pi over 2. Because the argument of the complex number I is pi over 2. Then we're going to have the two different cases, the k is 0 case and the k is 1 case. In the k is 0 case, we have cos of pi over 2 plus I sine pi over 2. And this gives us, when we compute it, gives us root 2 over 2, 1 plus I. And in the k is 1 case, we have cos of pi over 2 plus 2 pi now, because k isn't 0, over 2 plus I sine of the same thing, pi over 2 plus 2 pi over 2. And this gives us minus root 2 over 2, 1 plus I. So we have our roots here. The root of I is equal to plus or minus root 2 over 2, 1 plus I, which is completely consistent with our example above. Thanks very much for listening.